welcome to another AQA AS Chemistry video. Today I'm going to be doing a video on percentage yield and atom economy. I'll try and do this video relatively quickly, so I'll make this video extra long and unnecessarily long, I should say. Alright, go through percentage yield. The percentage yield of any reaction is usually less than 100%. The following 5 factors cause deviations from 100%. So first I'm just going to actually explain what percentage yield is. I'm not going to go straight into the video, but percentage yield, what it actually is it's being able to tell you how much of your product, so usually the mass, right? How much of your product, or the mass of your product, is formed relative to the mass that should have actually been produced. You may, if you could do a reaction, you may, if you calculate how much you should be producing, say you're meant to be producing 5 grams. In reality, you're not going to get, there's other factors that I'm going to list out that would prevent you from forming 100% of your product, such as side reactions, extraction, waste, hydration, incomplete reactions, and therefore you might actually only produce 4 grams of your product instead of 5 grams. The whole point of percentage yield is to try and tell you how much of your product they're actually forming relative to how much you were expected to form. And there's different things you could do to increase your percentage yield, which means that you're getting more value for your money. Realistically, this is good financially for companies, right? So the percentage yield for any reaction is usually less than 100%. The following 5 factors cause deviations from 100%. Side reactions, for example, side reactions. So there's unexpected reactions. Side reactions can happen, and this would mean that the intended product isn't created, and this reduces the percentage yield. So other products may be formed, and that would also reduce your percentage yield. Extraction, so it might be difficult to fully separate the product from the reaction mixture. Sometimes this happens during distillation, right? As I said before, when I was doing simple distillation, when you finally distilled your compound, it's not necessarily that 100% of your product is in the collection vessel. So if it's in your tap, you run your tap and you open the tap and you let your compound, let's say you're doing an oxidation reaction, right? You're oxidizing a primary alcohol to get an aldehyde, right? It's not that 100% of your aldehyde that's formed is necessarily, or that's now in your tap, that you've opened it, right? When you've dripped that down into an ice bath, it'll be like a beaker. So I was thinking about the word. It'll be a beaker that's in an ice bath, right? When you've collected it, usually what you do is you rerun your reaction again, because not 100% of your aldehyde is formed and is in your beaker. So you rerun the reaction again, because there might be some of that primary alcohol that's still there that hasn't been oxidized yet. So, and even after, when you've done it many times, it's still not going to be 100%. It's still going to be maybe like a couple of molecules of your primary alcohol, if I was doing that example. So extraction is also one thing as well that could reduce your percentage yield. Waste, so some of the chemicals will remain stuck to the glassware. Not Pyrex living, but the glassware is usually made out of Pyrex. So some of these materials can get stuck to the glassware. Pyrex is very good at trying to be one of the best. It's one of the best glassware that you use for chemistry, because they're very strong, and they don't actually tend to be that they've got quite a smooth, like, lubricant surface, so you can't really actually stick to one of this. I only found this out recently, but Pyrex is also useful because it's usually good for compounds that don't stick well to the glass, but it can still stick. Forget about the living part, but the Pyrex, so you usually use Pyrex that can actually reduce your percentage yield, but some of the chemicals will still remain stuck to the glassware. So if you're doing like a titration reaction, right, they usually tell you to wash the sides of the vessel, of your beaker. So if you're doing like a titration reaction, and you have to dissolve. I forgot what the first part of that reaction will be. Sorry, making a standard solution. That's what it's called. If you're making a standard solution, right? Yeah, I remember this part. If you're making a standard solution, you get however many grams of your compound. You usually measure out 3 grams, and you dissolve it in like 100 centimeters cubed of distilled water, and they tell you to wash the side of the vessel. That's because some of your solutes could have stuck to the sides of the vessel, and that means you're getting less than 100% of your actual value. So that's the reason why you have to always make sure you have to wash the sides of your vessel, or even, I keep saying vessel, wash the sides of your beaker, or even the volumetric flask. You wash the sides of that as well to make sure it doesn't stick to the sides of that, because all of these things would reduce your percentage yield. Right. Hydration. If a reaction is carried out in water, any extracted product may be wet. So this means that there's water in the extracted product. Water is generally extremely difficult to fully remove from a product. And if you get a percentage yield that's calculated to be over 100%, it's likely that your product is full of water. So for example of this is hydrous copper sulfate, or anhydrous copper sulfate, whichever one you're trying to make, right? If you get a bit of water that clumps to it, so if you get them seem clumping together, like if you get, you see this with any compound really, if you get them clumping together, if you get like soap, for example, that's just, if you get like the soap they use for hand washing soap, right? They use to like clean your clothes, hang outside. That soap, when you see them clump together, that's the water there. And if you was to compare the actual mass of it, and I compared the mass of it when it's clumped together, it will be more than 100% of what it's meant to be, because there's water there. And that water is increases mass. The extra mass is because of the water. And what they usually tell you, this can come up in the exam. They'll ask you a question like, why is the mass higher than it usually would be? And it's because there's extra water. And how can you get rid of the water? One of the reaction steps is to, and you'll do this when you're there's a practical where you have to make a pure solution, or like you have to use a bucket and a funnel. One of the steps is patting dry your compound with a towel, just patting it lightly, patting it down. You do that with your hydrous copper sulfate anyway. Like you still pat it down lightly after it's crystallized. You pat them down lightly with a dry towel. It's called blotting, right? You blot them dry, or lightly pressing on them to remove the extra water on them. So you're just getting a high percentage yield of your compound that's, without that water in there. And the last one, and usually this is the most common one, is incomplete reactions, which is incomplete reactions can happen because the reaction is very slow and hasn't been given enough time to happen. Hence why we try to get as many catalysts as we can for many reactions, so we can make sure that we don't have to wait a long time, and we're not getting incomplete reactions, right? We're getting most of a compound that's reacted. But if they're not, you still, that could happen, and you need to give your compounds enough time to actually react. Some reactions may require you to leave them overnight, and more time. This is usually the one that happens the most, and it's the one that's, you can see it, for example, any reversible reaction, for example the Haber process, right? But the reaction is, if the reaction is reversible, some of the products have turned back into the reactants. So with the Haber process, we told you all the reasons why, all the things that you could. I haven't made a video on the Haber process. Yeah, I don't think so. But if you remember from GCSE, it'd be like having I think it's an exothermic process. You'd have a endothermic reaction. I don't quote me, but if it's a exothermic process and you want to increase the forward reaction, yeah, you decrease the temperature. Yeah, you decrease the temperature to make sure that the forward reaction happens. No, I think it is an endothermic reaction. Don't quote me on that, but let's just say it's an endothermic reaction, right? And you have to you have to increase the temperature to a certain point. The higher the temperature, I think it is an endothermic reaction. So increasing the temperature, making that forward reaction happen more likely, or making equilibrium shift to the right to make that reaction happen more to make the forward reaction more likely. All of these things, all these things you can do, like, I think if you increase the pressure, that's another thing as well, because there's more reactants on the left side than the right side, or there's more moles of product on your left side than your right side. All of these things you could do to make your reaction go to the right hand side, right, or increase or make equilibrium shift to the right for these reversible reactions. When you're talking about reversible reactions, you're talking about the equilibrium. All of these things that you can make to force your equilibrium to go to the right hand side, is still a net. It's still a net value. It means the majority is going to that side. say it's all going to the right, it still doesn't mean that it's still coming to the left. Like, it's a net. It's like overall, there's more of the forward reaction than the backwards reaction, but the backwards reaction is still happening. It's just happening at a much lower rate than the forward reaction. So some of these things are very hard to get 100% certainty, like it's always going to be forward reaction, but you can, it's when you there are things they can do, like I said, by increasing temperature, and changing experimental conditions to make one reaction more likely to happen. But it's important to remember that the backwards reaction is still occurring. The backwards reaction is still occurring, and that would happen. That would cause some of that product to turn back into reactant, and you can still do the reaction again, and any reactant that's reformed, you can make it turn it back into product. But all of these things would reduce the percentage yield because there's less of your product, there's less of that product that you had compared to what you would expect to have. Alright, so calculating the percentage yield. The percentage yield of a reaction is calculated as the real yield divided by the theoretical yield multiplied by 100. So the actual yield over the theoretical yield times by 100, right? Actual yield over the theoretical yield times by 100, and that's all equal to the percentage yield. A comparison of the real and theoretical yields of a reaction. So a real yield is the amount that you've actually produced. So the real yield is the mass of the desired product obtained from the reaction. So it's the amount of that you've got. So when you've done your reaction, and this is how much you've weighed. So if I'm trying to produce copper sulfate, I've weighed out the mass of copper sulfate from the reaction. This is not what I theorize will happen. This is what I actually have. The theoretical yield is the maximum mass of a product that can or that could possibly be created from a reaction, and the theoretical yield can be calculated by balancing the equation if we know the mass of the reactants. So I did my previous video. I'll leave a link in the description of my previous video, which was about balancing equations, and this is why it's so important, because if you want to work at the theoretical yield, you need to be able to work at the moles from using that, and then once you find out the moles of your products, you can then work out the theoretical yield, which is the amount, which is the mass of a product that we should form. If all the experimental conditions were perfect, we would form 100% yield. This is how much mass we would expect. Let's say our theoretical yield will be 5 grams. We means that we've calculated that it's 5 grams, right? The real yield is what we actually weighed out, and it's usually less than 100%. So what we actually weighed out, we only weighed out 4 grams, right? So that means, and then your percentage yield would be 4 over 5 times by 100, and to get your percentage there, right? And that's how they would do it, all right? So I'm gonna start off. I was gonna start with a question, right? All right, first question, right? Read the question now. Try and do it yourself, and then I'll try and do it after. So pause the video now if you need to do that, and then answer the question. All right. A student wishes to collect the hydrogen evolved from a reaction between magnesium and hydrochloric acid. They add 1.2 grams of magnesium ribbon to 30 centimeters cubed of a 1.5 molar solution of hydrochloric acid. When you see this, it just means that just means moles per dm cubed. That's how they treat it, like moles per dm cubed, right? Sometimes it can be a bit confusing, but for someone that doesn't really know what it means, but that's the concentration of hydrochloric acid. Suggest how the student might collect the hydrogen evolved and measure the volume. Make sure to make specific references to the apparatus that you would use, right? So here's just experimental. This is something that you should know from GCSE. It's just a reaction of do you know the reaction? It's a practical that you should know about the magnesium ribbon. This is usually to find out the rate of reaction. If you do when I do year 2 chemistry, I think is it year 2 organic, no, year 2 physical. It's definitely year 2 physical rate of reaction. But this is one of the all right. So first of all, I'd conduct this reaction in a conical flask. So I then add a bung to the top of the flask after adding the reactants. So after adding the reactants, I should say immediately sorry about that. Immediately add a bung to the top of the flask. So immediately, for what I was going to say, that immediately add a bung to the top of the flask. Right? So if you can't read my handwriting, I'm just doing this quickly. That doesn't make it any better, to be honest, does it? Right. Connect the bung to a syringe to allow. So when you do this, the bung actually has a hole in it, so that's connecting the bung with the on the conical flask to a syringe to allow. It's a gas syringe, to be honest, to allow the gas to be funneled to the syringe. So connect the bung to a gas syringe, because we're collecting hydrogen gas, to allow the gas to be funneled to the syringe. And then the syringe will allow the volume of gas to be measured. So you can, in the exam, you can just bullet point these answers, right? There'll be probably, if it's 4 points they're looking for, it's 4 marks, 4 minutes to do the question. Try and do, if you could do it in less, do it in less. I was just trying to explain every point as I'm going through it, but you can just, try and do that try and do it in less than 4 minutes, so you can have time to do harder questions, right? So this is a 6-mark question, so I'll try and time it for you so you can do it in 6 minutes, right? But calculate the percentage yield of hydrogen given that 400 centimeters cubed was collected in the syringe. The AR of magnesium is 24, 6 minutes, right? So I'm going to set a timer for 6 minutes. I'm trying to explain and do it at the same time for 6 minutes, all right? So, 6-minute timer. Alright, cool. So calculate the percentage yield of hydrogen given that 400 centimeters has been collected in the syringe. AR of magnesium is 24. So first of all, I'd write out the rest. We have magnesium and hydrogen chloride. I'd write out the equation for it. So Mg solid plus HCl aqueous goes to form MgCl2 aqueous plus H2 gas. I know that's formed. Right. Balance this out. Sometimes if you can just see it, you can just do it straight away. There's one magnesium here, but I'll just do it right out this because this is how I said that you should do it. If you can't see it, I can just see it straight away that it's just 2 HCl. But just to show you, I can just see 1 Mg here, 2 H2s, so two hydrogens and 2 chlorides. I could just do it 2 here, but I could just show you. There's one magnesium, one hydrogen, one chloride, one magnesium, 2 hydrogens, 2 chlorides. Do this. We now have 2 on the other side. So our criticals. Now we've done that side. What we actually need to do now, we need to find the moles of hydrogen from the limiting reactant, right? I say the limiting reactant because you only have as much product as your limiting reactant allows. Because if you have an excess, if you have an excess of one compound, but you have a limiting reactant around this, it doesn't matter if you have an excess amount of this. Once this has been used up, once one out of 2 of your reactant is no longer there, it's been used up, there's no reaction anymore. If I have Mg left over but I have no HCl, the reaction isn't going to happen. So we have as many reactants as many products as our limiting reactants. So we have to find, in order to find the amount of limiting reactant, we have to find the moles of each. Which one gets used up first? So moles of Mg, moles of magnesium is equal to moles equal to mass of the MR. So it will be how much we have. 1.2 grams of magnesium, right? 1.2 over 24, and that's equal to 0.05 moles. So 0.05 moles of magnesium, moles of HCl is equal to we have 30 centimeters or 1 mole, right? Concentration is equal to moles over volume, therefore moles is equal to CV. So our concentration is 1.5 multiplied by 0.03 decimeters cubed, because it's 30 centimeters cubed is the same as 0.03 decimeters cubed, and that's equal to 0.045 moles. I should check this, but I can just see 0.045 moles. Now, therefore, because HCl is less, there's less moles of HCl than Mg, that means that, therefore, HCl is our limiting reactant, is the limiting reactant. As moles of HCl is less than the moles of magnesium. Alright, cool. Now we know that HCl is our limiting reactant. We need to find the moles of H2. So moles of H2 is a 2-to-1 mole ratio, right? 2-to-1 mole ratio. Moles of H2 is equal to 0.045 over 2, which is equal to 0.0225. Yes. Moles. They want us to work out the percentage yield right. So the moles of H2 is equal to that. Now we need to work out, we already have the moles now. We work out the volume. Right, so how do we work out the volume? We know that in 1 mole of any gas, this is a gas, right? 1 mole of any gas in at room temperature and standard conditions, which is this reaction is in. I didn't add it in, but I remember in the equation I had it in, it's in standard conditions and which is 298 Kelvin, 100 kilopascals of pressure. It occupies 24 decimeters cubed. You should know that from GCSE. 1 mole of any gas on the standard conditions will occupy 24 decimeters cubed. So we have 0.0225 times by 24, which will equal our volume. Volume would equal to N times by 24. And that's 0.0225 times by 24. and that's equal to 0.54, right? Equal to 0.54 decimeters cubed. And if we want to work out the percentage yield will just be, 1 second. The percentage yield is 0.4 over 0.54, because our mass, so our volume of water form is 400 centimeters cubed. So 0.4 is 0.54 times by 100. I'm just trying to make sure I'm wary of time. Is equal to 0.4 over 0.54 times by 100. 74%. 74.1%. As seen here. Alright. So I tried to do that in time conditions. I can do it in time conditions, but I was just trying to explain what's going on here. But as you can see, you can already see what's going on here really. It's just about being able to first of all balance your equation, then working out your moles using your reactants, finding out the limiting reactant, right? Limiting reactant, then knowing that in 1 mole of any gas in understanding conditions is on 24 decimeters cubed. Finding out the volume of our theoretical volume, right? And then using our actual volume of the theoretical volume times by 100 to get 74.1%. Okay, so the next question, suggest why the percentage yield was only 74.1%. Alright, pause the video now and try and answer the question. Alright, so the answer is just remember what we were talking about before, right? So that this is just what we had in up here, right? All the way up here about this waste, extraction, side reactions, hydration, incomplete reactions, like all these things. That's what you're talking about here, right? So some hydrogen might have escaped in the bung if the bung wasn't fixed tightly. Some hydrogen may have escaped between starting the reaction and fixing the bung. So as you're trying to remember, you're putting your finger you're putting your reactants putting your reactants in your conical flask, and you're trying to put the bung quickly, but some of it may have reacted and left the reaction fixture as you're trying to put the bung on, so that could have happened. And if it's not fixed tightly, that could also mean that some of your reactant may have left. Some hydrogen may have remained in the conical flask, because remember you put a pipe kind of like on your bung to try and connect and to kind of funnel your gas over, but some of it may still be in your conical flask, may not have funneled over, and not all of the HCl would have reacted. So this is an incomplete reaction. So not all the HCl reacted, meaning that not all the possible hydrogen was produced. Alright, so now we're going to go on to the next part of the video, which is about atom economy. So percentage of atom economy is the MR of your desired product over the MR of all your reactants times by 100, right? So this is just telling you, it's telling you how economical your reaction is. So if you're trying to produce a certain product, right, and you're trying to, let's say you're trying to produce, I don't know, you're just trying to produce a certain product, right? And you have CO2 or water as your side product, but there's many side products in your reaction. What you want to do, you want to limit the amount of side products in your reaction, because they're just waste. You don't actually need them. Ideally, if you want to have 100% atom economy, which is possible, it's possible to get 100% atom economy, right? Think of any reaction that only has one product, right? Like magnesium and chloride. If you have magnesium and chloride and you did the reaction together, MgCO2. If you had, for example, photosynthesis, right, O2 is a side product of reaction. Therefore, what we're trying to produce we're trying to produce glucose there. We're trying to produce the glucose as a product, as the only reaction, but only oxygen, which is helpful for us, but technically for plants, oxygen is a side product, it's not needed. So the whole point of doing atom economy is that before you do your reaction, you can tell how economical your reaction is, that how much of your actual product you're making. If you're making more side products than reactants, so more side products than your actual product or desired product, your atom economy would be very low, because it's the MR of your desired product over the MR of all your reactants. Right, so they're going into the reaction pathway. And also that when you're doing the MR of all your reactants, that includes the mole. If you have like 2 moles of water you're using in your reactants, you would include that when you're doing the MR of your reactants. Right. So reaction pathways or ways reactions can happen with high atom economy, which is the percentage of useful products made, are good for 2 reasons. For cost, so using the smallest possible mass of reactants would reduce costs, and waste. A high atom economy means that less waste is produced, i.e. efficient, as you're making the most out of your costs, so they're more cost effective. And finding ways to make waste products of chemical reactions useful can increase the atom economy. I have an example of this, but I'll do that in another video. Hopefully this video was helpful. I know I stutter a lot, I am trying, but I'll get there. I'm taking steps. Alright, that's it.